In today's video notes, we are going to discuss polynomial functions, and this is our learning target. I'm going to have you read the learning target, and I'm going to ask you a question over the learning target in today's notes. So let's first look at page 299, where it talks about what is a polynomial function. And so this is the textbook definition of what a polynomial function is. And essentially, when we look at a polynomial function, there are certain key features that we should be able to identify. We should be able to identify the leading coefficient. And so when the polynomial function is written in order from highest degree or highest power, from highest to lowest, then that first coefficient is our leading coefficient. We should be able to identify what each term is, whether we have a cubic term, a quadratic term, a linear term, or a constant term. And we should also be able to identify the y-intercept. And so if there is a constant term, that's the y-intercept. Now, polynomial functions are not limited to this. You know, they may not be 4 terms. Any function that meets this definition that has a degree that's a non-negative integer, so the exponent has to be non-negative, is a polynomial function. And so all of these are polynomial functions. We have monomials, which is just a single term. Those are polynomial functions. We have binomials. Those are 2 terms. That's a polynomial function. So all of these are polynomial functions. So they don't have to be 5 terms like that previous example on page 299. And the degree of the polynomial function is based on the variable term. And so if we have a constant polynomial function with just a numeric value, then the degree is 0 because there is no variable term in the expression. In a linear polynomial function, here we have a degree 1 because there is only one variable term and its exponent is a 1 because we can't, it's like an imaginary 1, we can't see it. So this would be a degree of 1, which makes it linear. In a quadratic polynomial function, we have a variable term whose degree is 2 for squared, and so since that's the highest degree or highest power, then we call it a quadratic polynomial function, and so on. So the degree is based on the highest power or the highest exponent in that polynomial function. And so still on page 299, these problems are not there. These are just examples of how we classify a function to be a polynomial function or not a polynomial function based on the definition. So for a polynomial function, the power, which is the exponent, says the power of each term must be an integer greater than or equal to 0. And the coefficients can be real or imaginary. So, and these two, f and g, these are examples of polynomial function. Here we have the square root of 5x to the 4th minus 2/3 x squared plus 6, where each power, so 4 and 2, they're integers greater than or equal to 0, so they're non-negative, and the coefficient, square root of 5, negative 2/3, and also the 6, those are all real numbers. And in G, we have cubed, squared, and then to the first power, so those are non-negative integers, and 4, negative 2, 5, negative 1, and even all of those are divided by 17, those are real number. So we don't have an example with an imaginary number, but these represent a polynomial function. For this example, it's not a polynomial function. Well, the degree is still even. It's not even. The degree is still non-negative here. It's non-negative here, and it's non-negative here. But in the denominator, because I'm dividing by x, this is really, well, I guess I'll write it down. I just won't say it. I'll write it down. So if I were to simplify this, this is the same as me saying 4x cubed divided by x, and then 2x squared divided by x, 5x divided by x, and then minus 1 divided by x. Well, I can simplify that further. This would be 4x squared minus 2x plus 5, and then finally minus x to the negative first power. And so here we have a problem. We have a variable term that does not have a non-negative integer as its exponent. So because this creates a term whose exponent is not greater than or equal to 0, that's why it's not a polynomial function. So yeah, hopefully that makes sense. If not, feel free to stop and ask, or feel free to ask me in class if you watch this video at home. So on the next page, on page 300, on page 299, I want you to look at those two problems, A and B, and see if you can determine if one, they are a polynomial function, yes or no, and then what's the degree, what's the leading coefficient, and what's the constant term if it is a polynomial function. So for A, you should have said yes, it's a polynomial function, it meets the criteria. The variable terms have a degree that's greater than or equal to 0, and then the coefficients are either real or imaginary, so yes, it is a polynomial function. The degree is based on the highest power or the highest exponent in the entire expression. So here our degree would be 3. The leading coefficient goes with that highest degree, so it would be the square root of 3, and then the constant coefficient, which is the constant term, is the term without the variable, and that's negative 1/6. So what about part B? Part B has this problem, or this expression, and we would like to determine if it's a polynomial function. Does it meet the criteria we talked about earlier? No, it does not. Because it's not a polynomial function, then we don't have to worry about degree, leading coefficient, or constant coefficient. Here, 7 divided by x is the same as 7 times x to the negative first power, or negative 1 power, and so that makes it not a polynomial function. So if we turn the page, we have another example, which is example C. It says determine which functions are polynomial functions, and so if they are a polynomial function, you want to identify that information. So with this one, we can do the same thing. Is this a polynomial function based on what we just talked about? Now, you can actually take this 9 and divide each of these terms by 9 if you wanted to. It doesn't really change the value, but it will help you get your leading coefficient. It will help you get the correct leading coefficient. And also you want to make sure that you rewrite the polynomial function in order from highest degree exponent to lowest degree exponent. So I don't want you to think that just because this is written first that it's the leading coefficient. It's really not. It goes with whatever the highest degree exponent is in the expression. So yes, it's a polynomial function. Each of the exponents are non-negative values. They're all greater than or equal to 0. The degree would be 4, since 4 is the highest. The leading coefficient would be 7/9, since it's the coefficient of the term with the highest degree. And the constant coefficient would be 0, because there isn't one in the problem. All right, power functions. So power functions help us kind of visualize a graph. Most of us are familiar with the first 3 power functions, which is linear, quadratic, and cubic. Linear has an exponent of 1, so it just creates a line. It crosses the x-axis at most in one place. And then quadratic functions, the squared term is what creates the parabola or the U-shaped graph, and it will cross the x-axis at most in 2 places. And then cubic functions, it's kind of like a curved line, but it will cross the x-axis at most in 3 places. This one only crosses once, but you can have up to 3 intercepts with the cubic function. So the degree will help you determine the most number of times it could cross the x-axis. Now anything above 3 is just an iteration of quadratic or cubic. So if you look at a quartic function, which is to the 4th power, then it almost looks like a parabola, but where the vertex would be is more kind of squared out a little bit. And so this will cross the x-axis at most 4 times. Here it just touches it because there's no other terms, but if it had other terms, then you could see up to 4 x-intercepts with this one. With this function to the 5th power, I think it's quintic, it will cross at most 5 times because it has 5 possible zeros. But this one only passes through the origin, just like this one does. But it has a similar shape as this. So when we look at to the 6th power, it'll create kind of a parabola-ish shape. and then to the 7th power, it will look cubic in nature, and so on. So we can use the power functions to help us graph other polynomial functions. So here we want to use transformations for example number 2 on page 300 and page 301. We have 3 graphs that we would like to talk about graphing, and we can also discuss transformations at the same time, since we looked at that in the previous unit when we took that test in chapter 3. So we know that this is negative x to the 6th power. So if I'm going to graph that, I can look at x to the 6th power, which is the power function, and then the negative tells me to reflect that across the x-axis. And so this would be the graph of negative x to the 6th power. And mainly with graphing, I don't want you to be too stressed or concerned over graphing, because you can use decimals, which is fine, but we still want to be able to describe what's happening in the graph. So by now, hopefully you should be able to look at this and tell that it is reflected across the x-axis versus being reflected across the y-axis. With this one, the power function would be x to the 5th power, and then we have 2 transformations going on. We have something being added to the x on the inside of the parentheses, that's being to the 5th power, and then we have 2 being added to the entire function. And so those 2 things cause a shift, but do we know what type of shift those 2 things cause? So if I look at the graph here, the blue one would be the power function, x to the 5th, so it looks cubic in nature. It's a little more flatter here where it crosses the x-axis. And then the +1 is going to cause a horizontal translation to the left. So that gray line that you can barely see would be the horizontal translation. And then the +2 causes a vertical translation or vertical shift up. And so that's what the red line is. So hopefully we can start to recognize these transformations, because we spent part of that chapter 3 talking about it. And so your last one that you are expected to graph or use transformations to sketch, we would use the quartic power function. So 2 times x minus 3 to the 4th power. And then we look at where there's 2 things happening here. In the parentheses, we're subtracting 3 from x. So that does something to that power function, or to the, I guess, the parent function of x to the 4th power. And then we're multiplying it by 2. And so do we remember what those 2 things are? So here's my, the blue one, again, is the power function, x to the 4th power. It looks quadratic in nature, but we know that it's a little more flatter here because of the 4th power. And then the black kind of grayish line would be just x minus 3 to the 4th power. So it's being shifted 3 units to the right, because the 0 is changing. The location of where that vertex is sitting is changing. And then the red line, which is just ever so slightly on the inside of the gray one, well, that's because this power of 2, we're multiplying all the values by 2, so they're stretching them up. It's a vertical stretch because it's getting a little narrower. So those are the 2 transformations that we would have need to have recalled from chapter 3 for part C. So now we talk about end behavior. So I know in Algebra 2 you spent some time discussing end behavior, and mainly with this, on page 301, you can jot this down if you would like. I know it's a lot of information. But when we look at end behavior of polynomial functions, we mainly just focus on the leading coefficient. So here on the right, I have one polynomial function, which is this here, x to the 5th minus 2x to the 4th minus 6x cubed plus 8x squared plus 5x minus 6. And mainly, I'm comparing that to y equals x to the 5th power, this power function, because they have the same end behavior. Ultimately, the only difference is here in the middle, they differ because this is a single term versus this has, 6 terms. And every term after x to the 5th is what affects the shape of this graph, because this is the generic or the general shape, and then all these other terms affect that shape. But when we look at end behavior, we look at, well, what is the right hand and the left hand side doing? And in both of these graphs, the right hand side of this polynomial function and this one, they're the same. And the right hand side of the graph are also or this is the right. The right-hand side is the same, and the left-hand side is the same. So when we want to discuss end behavior for any polynomial function, we want to look at its basic power function to describe that. Or we just want to look at the leading term is what we want to use to determine the end behavior. And so for this particular end behavior, it is decreasing on the right, or it's decreasing on the left. I'm not sure why I'm mixing up my left and my right today, but it's decreasing on the left and then it's increasing on the right. And so another thing that we want to look at for determining end behavior of polynomial functions is a little bit of a two-step process we're going to look at. We still just want to focus on the leading term. So here, and we want to look at the leading coefficient to determine, one, is it positive or negative? So that affects if it's been reflected or not. And then we'll look at the degree. And so we look at those two things, the leading term to determine how the right side finishes. So if the leading term is positive, that means the right side is always going to finish up. If the leading term is negative, it's going to finish down. And kind of a visual of that, well, I'll show you the visual in just a moment. So that's step one. And that you can write on page 302 if you're taking down some quick notes. For step two, we look at the degree. So if we have an odd degree, like x cubed, x to the fifth, x to the seventh, then it's either going to be one of these two scenarios. It's going to go in opposite directions. It's either going to start low and end high, or it's going to start high and end low. So that the graph will start and finish in opposite directions if it's an odd degree. If it's an even degree, and this, both of these depend on if the leading coefficient is positive versus the leading coefficient is negative. So if it's an even degree, if the leading coefficient is positive, well, then it's going to go in the same direction. It's going to start high and it's going to end high. So they're going to finish in the same direction. If the leading coefficient is negative versus being positive over here, then it's going to be decreasing. So regardless, if it's an even degree, it's going to finish in the same direction. And so what that looks like is, well, you have that, but for a moment, I'm going to take a little break from this. So if I go over to Desmos, and if I look at, let's just say negative 2x to the fifth power. So this negative 2, if I were to compare this just to x to the fifth power, so here's the parent power function for x to the fifth power. And notice they're going opposite directions. So this is going towards negative infinity. This is going towards positive infinity. But that negative 2 makes it finish in opposite directions. So it starts at positive. It starts on the positive infinity side. So this is increasing without limit on the negative side, but it's going up. And then it's decreasing over here when the x values are positive, is going down. So similarly with the, let's say, x to the sixth power. So this is the sixth degree power function. And if I make that, let's say 5x to the sixth power. So it's the same direction. It's just a little narrower because of that vertical stretch. And if I make that negative, so negative 5 to the sixth power, it just reflects across the x-axis, and now they finish in the same direction. So that's just like a little takeaway that we want from being able to observe the graph. So with this example on page 302, it says use end behavior of each graph to determine whether the degree is even or odd. So based on which way the ends go. So is graph A an even or odd degree? Or is graph B even or odd? So basically, is when you look at, if we knew the equation, if you look at the highest exponent or the highest degree term, is it a number divisible by 2 or not divisible by 2, even or odd? And then is the coefficient positive or negative based on where it starts and finishes? So with A, you should got odd degree because they are in opposite directions. Only odd degree functions looks like this, where we have the x cubed, x to the fifth power, x to the seventh power, and then this would be leading coefficient as negative, because if I look at x, if I compare this to x cubed is something like this. So I can do that. And then for the other one, of course, that would be an even degree, because the endpoints go up in the same direction, and the leading coefficient is positive because they finish up. So and again, I can compare that to x squared. So x and y intercepts, moving along so we can make this as short as possible. Page 303, finding x, y intercepts. So far we found x and y intercepts probably in every single chapter we talked about, and it's no different. To find the y-intercept, we replace the x's with the 0, and we evaluate that. To find the x-intercepts, we set the function equal to 0, and we factor or we solve in some way to get the x by itself. So, or we can graph it. Those are also, that's also a valid way to find the x, y intercept. You can also graph it as well in Desmos. So if we look at this example on page 303, it says find the intercepts of the polynomial function. So we want to find both the x-intercept and the y-intercept. So I'll do the x-intercept first. I'm gonna remind you how to graph, but you can also graph this in your calculator, or you can graph this in Desmos. But here's the function. I know if I want to find the x-intercept, I need it to make the f of x term, which is y, equal to 0. And then you can actually factor this by grouping. So I can group the first two, and I can group the last two. If we group the first two, I notice that x cubed and x squared each have an x squared term in common, so I can factor that out. And that leaves me with x minus 1, because x squared times x is x cubed, and x squared times 1 is x squared. And then the second two, they each have a 4 in common. I'm actually going to factor out a negative 4. So if I divide out a negative 4 from this term, then that just leaves me x. And if I factor out a negative 4 from this term, that leaves me minus 1. So if I redistribute, negative 4 times x is negative 4x, negative 4 times negative 1 is positive 4. And I can bring those outside terms together. So that gives me x minus 1, that brings that together. And then x squared minus 4, bring that together, equal to 0. And now I can figure out what the value of x is for my intercepts. I can set each part equal to 0. And when I set each part equal to 0, I get 3 x-intercepts. I get x equal to 1, x equal to 2, x equal to negative 2. The y-intercept is a little more simple. I take this function and I replace the x with the 0, which means I take each x value, replace with 0, and just evaluate, and we get 4. So my y-intercept is 4. And what this does, when we graph, or if we were to graph by hand, we have an idea of how the function might look. So I know these are my x-intercepts, so negative 2, 1, and positive 2. That's my y-intercept. And because of the degree of 3, I know what the end behavior should look like, and it's positive. So I know it should start going to negative infinity because it's positive, and then it should end going on positive infinity because the leading coefficient is positive. So the purpose of that is that we get an idea of what the graph might look like, and of course we can graph it in Desmos or our calculator, and we can get an actual idea what the graph looks like. But in your homework is going to have you do some sketches of the graph, and so this is a way that we can find the intercepts. And maybe not all the intercepts are going to be integers, so we can always go with factoring, quadratic formula, stuff like that to find the intercepts. So now if we look at page 304, we begin to talk about factors of polynomial functions, and then eventually what a multiplicity is. So in this particular section, determining the real zeros of a polynomial functions and their multiplicities. So we should know that if this is a factor, so if x minus c is a factor, so here in my little images down here, if x minus 1 is a factor, then x equals c is a 0. So basically that just means if you have the factored form of a polynomial function, then this is the 0 of that function when you solve it. So x minus c. So here, since x minus 1 is a factor, then the 0 is where it crosses or touches the x-axis. And so here we can see that the 0 is just positive 1. That's essentially all this means. And in that blank that you fill in your guided notes, it's the part in red. And in the next blank, this would go in the next blank. So here we look at if x minus c to the kth power is a factor of a polynomial function where k is a positive integer, then k is the multiplicity of x equals c. And so if I look at those same two examples that we had in the graph, the polynomial function was f of x equals x minus 1 squared. So if I were to solve this for x, set it equal to 0, I get x equal 1. Well, we say that x equals 1 has a multiplicity of 2. And in the polynomial function, x equals, or f of x equals x minus 3 cubed. And if I solve that for x by setting this equal to 0, so take the cube root of both sides and then add 1, then we say that it has the multiplicity of 3. And so what well, I'll talk about that in just a moment. So in your next two blanks on page 304, it goes on to talk about how the graph might look based on the multiplicity. So again, if x minus c to the kth power is a factor of a polynomial function where c is a real number, so this is a real number, and k is an integer, this is an integer bigger than 1, greater than or equal to 1, then if it's an odd number, if this power happens to be an odd power, then the graph will always cross at c. So we'll always pass through the x-axis at whatever number this is. If k is an even number, so we have the same situation. So if I have this is a factor, x minus c to the kth power is an even number, then the graph will just touch at the x-axis. And that has to do with when we talk about multiplicity, which is the a multiplicity is just the number of times that that factor is represented in the function. So if I have this function here, x times x squared minus 1 times x minus 1, and if I factor x squared minus 1 to x minus 1 and x plus 1, I can regroup this x minus 1 and this x minus 1 together, and I see that if I were to, solve this polynomial function for its x-intercepts, so set each part equal to 0, then of course that stays the same. This is x equals negative 1, and this is x minus 1 times x minus 1. I guess I really didn't have to regroup that together, so I probably, yeah, that's okay. So this is x equals 1, and this is x equals 1. So this x equals 0 is only represented once in the polynomial function, so it has a multiplicity of 1. This x equals negative 1 is only represented once in the polynomial function, so it has a multiplicity of 1. And then this x equals 1 has a multiplicity of 2 because it's represented twice in the polynomial function. And you don't have to really solve it to get that. You can look at the degree. So the x equals 1 comes from the x minus 1 squared, and so its multiplicity is 2 because of that as well. And then, of course, this has a degree of 1, so its multiplicity is 1. And then this one, which x minus x equals negative 1, comes from this factor. It has a degree of 1, so its multiplicity is also 1. So you could do that as well to figure that out. And when we look at the graph of the image, so I graphed it in Desmos. Back to what we talked about, since these two are odd multiplicities, at 0, since it's odd, it crosses at that number. And then at negative 1, since it's odd, it crosses at that number. But if you look at positive 1, since it's even, it just touches it. And that's like a double root. So that goes back to like a quadratic function. So it's quadratic in behavior at that location. So that's just kind of connecting things from, algebra 1, maybe algebra 2, and then the kind of middle part of the video. So we take that same graph we looked at earlier, and then we can talk about how to graph it better. Now that we have some more information, we can talk about how to find test values for turning points, which I don't want to, I guess, overwhelm you. Hopefully you're not already overwhelmed. But ideally what we would like to determine is, based on the x-intercepts, which was negative 2, 1, and positive 2, for this function we looked at earlier, how would, other than graphing it in the calculator, which is perfectly fine, or on Desmos, how do I know that it's going to go up and then cross, and then is it from here, is it going to go up, or is it going to just go slightly up and then cross through the 4? So we look at test values to help us determine kind of how the graph might look. And so here we choose a value between -2 and 1. And we chose, or I chose -1 to figure out, because it was kind of, I chose between -2 and 0, because this was one of the points. You try to figure out the points on the graph and find test values between those points. And then I chose a test value between 1 and 2 to figure out how low it would dip here. And so that just helps us get a more accurate depiction of how the graph might look. And of course, you can always sketch it or graph it in Desmos, because that's very user-friendly. One thing we want to talk about, since this graph doesn't have an actual maximum or minimum, because it continues to go on in both directions till it without end, we talk about at the turning points. Well, for one, the graph has at most n-1 turning points. So all polynomial functions of any degree, you take that degree and you subtract 1 from it, and that's the number of turning points. So if I go back, this was degree 3, so it has at most 2 turning points. So here it increases, and then here's a turning point, it decreases. And then here's another turning point, it increases. So at those turning points are considered a relative maximum or relative minimum. The relative maximum occurs when it goes from increasing to decreasing, and the relative minimum occurs when it goes from decreasing to increasing. So here, this was a relative maximum, kind of, because we're not really at the maximum point. As you see, it's a little over. The maximum point is actually a little more to the right, but somewhere around -1 is the relative maximum, because it goes from increasing to decreasing, and then somewhere around 1.5 is the relative minimum. And these are the 4 steps we look at that we've kind of talked about if we want to sketch the graph of a polynomial function. So determine the end behavior, plot the y-intercept on the graph, replace x with 0, factor it to find all the zeros and their multiplicities. The zeros help us determine where the polynomial function crosses or touches the x-axis. The multiplicities help us determine, did it actually cross at that location or did it actually touch? And then we want to choose some test values between each 0 to figure out, is our graph above that interval or below that interval? And so now the rest of the video is going to be for you to try some problems to see if you can sketch the graph. But I'm mainly going to ask some questions about can you find the zeros and multiplicities? So for these 2 questions, I'm going to ask you about zeros and multiplicities, because you can certainly sketch that in Desmos. And then, well, there's the graph. And then on page 309, you're given a graph. From that graph, can you determine if the degree was even or odd? Is the leading coefficient positive or negative based on what we talked about? So can you do that on page 309? And then there should be, I believe, 2 more questions. So what's the value of the constant of the coefficient? And then can you identify any of the real zeros and state their multiplicity based on how the graph looks?